Welcome to Chapter 15 on interference and diffraction. We're only going to be covering 15.1 and 15.2 and will not be doing any calculations with this section. So what we're going to do first is we're going to describe how light waves interfere with each other to create something called bright and dark fringes. We're going to describe what an interference pattern looks like. And then last, we'll explain what diffraction is and how interference patterns are an effect of diffraction through narrow openings or passing around obstacles. So looking at interference first, that comes from 15.1, and we're only covering page 526 and 527. So the question is, what is interference of light? So before we answer that question, you might want to think about what we learned about interference of sound, because remembering how interference of sound work will help us understand how interference of light works. So the definition is interference works like with mechanical waves, okay? It's the way that waves add or subtract from each other to create a resultant wave. Okay, so the resultant wave of interference is the sum of the waves interfering. And you can see everyday interference on things like this is a soap bubble. Okay, you can see it when you see oil on the street over water, right? That gets that very colorful pattern. Picture that's showing us what happens. Okay, you can see all these different colors, and the way that they interfere, we get all this different color, and it just depends on the way that the material is. So taking a closer look at interference. Okay, this should be review, right? So when waves, their peaks line up, okay? So if their peaks line up, so it's peak to peak, it will add up and give us a bigger wave, right? And this is called constructive interference, right? And when it's peak to trough here at the same point, we get destructive. So hopefully that's review. And what your book does in this section compared to sound is it goes a step further, and it just shows you if you have two waves with two peaks of different amplitudes, they just add up to give you a third one that's even bigger. But you can have some destructive interference where one wave is smaller than the other in amplitude, and you will get a wave that is just weaker than the bigger one total. So we don't have to have complete destructive interference to have interference. So with that, okay, this is an example of what it can look like if we use a single color of light, okay? So if we have a single color of light going through two different slits, right? So their patterns will reach different places, and we end up with these bright spots, okay? So these bright spots, called a fringe, a bright fringe, okay, is where we get constructive interference, and the dark spots here is where we get destructive interference, and it happens because the waves overlap, okay, and at this part, right, the dark fringe, we're going to get waves that cancel out, okay, and at the bright fringe here, we get waves that add up, and they're in the same direction, okay, so the interference changes the brightness of a light, okay. So here's just showing you with a single slit, right, you get this pattern. With a double slit, you get these really clear defined things, and that comes from the interference. Okay. So here it's just showing you here the difference between a one color, this is called monochromatic, mono meaning one, chromatic having to do with color, and I'm running out of room here, so I'm going to write it sideways. Okay, so monochromatic means one color. Here, in this other one, here, we're seeing a multiple color interference pattern. So white light can still interfere, but what happens is because you have different wavelengths of light, right? We have different wavelengths. They all have a different one. And so what happens is they're going to interfere at different places. So where we see this red spot, what might be happening is all the yellow and the blue light is canceling out, and it's at a destructive interference place, but the red here is at a constructive interference place, and so we just see the color red. And the same thing happens for blue and yellow and all the other colors here. Okay, so that's how white light can interfere. With this, I want to point out this fact that light can interfere like this. This is one good example that light is a wave. Okay. There used to be a debate about this. They used to think it could be a particle, and they're like, well, is it a wave or is it a particle? Okay, but this here, interference patterns, and what we're going to look at in a minute, the diffraction, are both proof that light is a wave. So that's what this experiment shows, this shining the light through a slit. It shows us that light is a wave. Okay. So here I just want to point out that the width of a fringe depends on the wavelength of the light, okay? And different colors produce different interference patterns. So if we look at this, we can see that this first set of bright spots, right, is this wide for the red. It's a little narrower now for orange, and it's the narrowest for green. Okay, so that happens because we have different wavelengths of light. Okay, so it's going to add up and subtract in different amounts at different places. So this brings us to the end of interference then. And so now we're going to move on to diffraction. So diffraction is from section 15.2, and it's going to cover these pages, 532 to 535. And there's a little bit of math in there, but remember, no math. So what is diffraction? What does diffraction mean? Okay. Well, what happens is diffraction is the change in direction of a wave due to an obstacle, opening, or edge. So if we took some waves and just sent them through, okay, and this is, remember, what we're seeing, these lines represent wave fronts, or the peaks of a wave. So I could draw little tiny waves here. It's not perfect, but you get the idea. And as it goes through, what happens is instead of going out, we could imagine there's a nice straight line here like this, right? But instead of those waves just going through and traveling in that straight line, what we get is this pattern here that you see where they start to spread out. Okay, so we don't get the straight lines and they spread out. This bending of the wave, or the change in direction, okay, this is what diffraction is. And we can see this in all kinds of waves. It's a characteristic of all types of waves. And so if you look in this picture down here, this is a satellite picture looking at the ocean, right? And so out here we just have normal waves, and there's not really a big pattern to them besides the normal. But when these waves come in here, okay, so they come in through this rock and this rock, what happens is it starts to cause the waves to diffract. And so you start to see this kind of curving pattern that happens. And you can see that now you get this pattern of curved waves that go through. And you can even see it a little bit curving around that rock, and you can see it curving around this one too as it comes in. And so this is what diffraction is this bending or this change of direction due to any obstacle, opening, or edge. So going back to these pictures of the different colors of light interference and why exactly they're different has to do with the diffraction. Okay, so the width of fringes depends on the wavelength of the light. So this is because light bends different amounts due to its wavelength. Okay, so short wavelength light will diffract or change direction less compared to longer wavelengths of light. So we can tell from this picture because green light changes the direction the least, it's the narrowest, okay, and red is the biggest, that green has a shorter wavelength of light than red has, okay, and orange is in between them. So this is actually one of the first ways that they could start measuring what the wavelength of different lights actually is using this knowledge. Okay, so here's another example that shows the difference, okay? So here, when we get a pattern from a single slit, you still get an interference pattern because of diffraction. Okay, so before, when we were talking about interference, we were using double slits that clearly gives it. It's not as clear with this, but you still get dark fringes and light fringes. Now, but when we take that width of that slit and we make it a lot narrower, so this slit is much narrower than this one, then you get much more defined patterns of interference, okay? And this is because of the diffraction. The wavelength is going to change much more sharply going through a narrow slit because light has a small wavelength. Whereas if you make the slit wider, it's going to bend less. And so we end up with this kind of hazy redness and not as defined bright and dark patterns. So that's why we get these two differences in our interference pattern. So the last thing we need to talk about with diffraction is something called diffraction gratings, okay? Because they are something that has many tiny ridges that are sized to cause the light waves to bend. So they can be used to separate white light into its components of the different colors. So an example is this. This is what a grating would look like if you zoomed in really close to it, right? So you have white light coming in, okay, and it hits this grating, and these edges are really, really small, okay, so that they can actually change the direction of light. And because each of the different colors have different wavelengths, then they bend different amounts, and we get this kind of rainbow effect over here. So this is actually also how 3D glasses, they work like this. When you're seeing a 3D movie, the movie is shown in different colors, and then when you watch it through the different diffraction gratings, what it does is it tricks your eyes into thinking that it's seen in 3 dimensions instead of just 2. So the key here is to remember that each different wavelength will bend a different amount, and this allows us to see the components of light. Okay. Another thing you can see is CDs. CDs are made from bunches of tiny holes and ridges, essentially, and so that's why they look like a whole bunch of different colors. It acts like a diffraction grating. The other way that diffraction gratings are used is they can use to identify elements and stars, because each different element has an identifying color. So as light shines from a star, it looks white to us, but if you use a diffraction grating, you can see it separate into specific colors, and the different colors that it separates into will tell us what element that star has, because each element has an identifying color. So that brings us to the end of diffraction gratings and chapter 15. I will see you guys in class, and let me know if you have any questions.